Okay, so we're going to look at a really interesting property of proof by induction that might seem a bit counterintuitive at first. So if we look at proving each of these two inequalities, have a think which one should be more difficult to prove. You can see they're almost the same inequality, but here we've got 1 plus nx and here we've just got nx. And I think to make this really clear which one is going to be easier, let's just replace these with some numbers. So this is like having the first one, if you imagine we were trying to show this was greater than or equal to 6, then the second inequality would be analogous to showing this was greater than or equal to 5. And if you want to show that something's greater than or equal to 6, this should actually be harder than showing that it's greater than or equal to 5, because to show it's greater than or equal to 6, you'd have to rule out some numbers like 5.5, for example. And if you look at this on a number line, I think it becomes even more clear that if you want to show something's greater than or equal to 6, you'd be showing that it belongs in this region, whereas if you're showing that it's greater than or equal to 5, you've got a larger set, so it's a weaker claim. And similarly here, this showing that 1 plus x to the n is greater than or equal to nx is actually a weaker claim, and in theory should be easier to show than the first inequality there. So we'll have a look at the proof by induction for this first case, and then we'll look at using proof by induction for the second one as well, and we'll see what goes wrong. So for our first scenario, we could use n equals 1 or n equals 2 to show that the base case holds. So with n equals 1, you literally just get 1 plus x is equal to 1 plus x, and this holds quite trivially. And then for our proof by induction, we'll assume that this statement is true for n equals k. So we'll let 1 plus x to the power of k be greater than or equal to 1 plus kx, where k is greater than or equal to 1. Then what we want to show now is the exact same, I'll just put want to show here, the exact same result, but now instead of with k, we want to show this with k plus 1. So 1 plus k plus 1 times x. So we can take our first inequality, and all we'll do is multiply by 1 plus x on both sides. So here we're working with x greater than or equal to negative 1, so we're allowed to multiply by something that will be positive on each side of this equation, this inequality. So multiplying by 1 plus x, we get on the left-hand side, now it's 1 plus x to the power of k plus 1 is greater than or equal to 1 plus kx times 1 plus x. Then we can expand the brackets on the right-hand side here. Our constant term is just 1, and then our power of x term, we've got kx, and we've also got plus another 1 times x, so plus k plus 1 times x, and then finally we've got the kx squared term as well, so plus kx squared. And now k is positive, and so is x squared, it's just a real number squared. So this term can be removed now, and this is greater than or equal to 1 plus k plus 1 times x, which is actually exactly what we were trying to show. We started with this statement true for some value of k, and then by multiplying by 1 plus x on both sides, we've managed to show that the same statement is true where we've replaced k by k plus 1, and this would complete our proof by induction then. So this has worked perfectly fine for our first inequality. So now let's see what happens when we try to prove the second, in theory easier, inequality using induction. So just like before, our base case where n equals 1 is really easy to see that it's true for this inequality. We have 1 plus x to the power of 1 is greater than or equal to 1 times x. So we just have 1 plus x is greater than or equal to x, which is certainly true for all values of x. And similarly for n equals 2, you can show this quite easily just directly. So going into our proof by induction, we're going to again assume that this result holds for some value k now, that this is greater than or equal to k times x, where k is greater than or equal to 1, and again x is greater than or equal to negative 1. So now we want to show that the same thing is true where we replace k by k plus 1. So we want to show that this inequality, we've got the power of k plus 1 is greater than or equal to k plus 1 times x. So if we follow the same procedure as before, multiplying on both sides of the inequality by 1 plus x, which is again non-negative because x is greater than or equal to negative 1, we're going to get 1 plus x to the power of k plus 1, just like before. And now this is greater than or equal to kx times 1 plus x. And when we expand the bracket here, we get kx plus kx squared. And this doesn't quite look like what we're aiming for. We're trying to show that this is greater than or equal to k plus 1 times x. And you can actually show that this is not always greater than or equal to k plus 1 times x, because k plus 1 times x, if we expand the brackets here, this is kx plus x. So we run into a problem actually when kx plus x is bigger than kx plus kx squared. So I'll rewrite this, and we can subtract each of the kx's here. So this fails effectively when x is bigger than kx squared, like this, because then your x would be bigger than the kx squared. So this kx plus kx squared term wouldn't be greater than or equal to k plus 1 times x. So we can rearrange in this inequality. This is saying it fails when x is bigger than kx squared, and rearranging here, this tells us this fails when x is less than 1 over k. But this is a really big problem now, because k was just some integer greater than or equal to 1, and we're trying to show that this inequality holds for all x greater than or equal to negative 1. So we've tried to follow the same sort of proof by induction and the same steps as we did for this actually slightly harder inequality to show, and we've run into a problem and the proof has failed there. So what's gone wrong? Well, the issue, if you compare the two inequalities, is actually when we do our proof by induction, our inductive hypothesis in the second case is much weaker than we had for our inductive hypothesis in the first case. So now we've got a much weaker statement to build upon, and actually this inductive hypothesis is so weak that following the same argument as we did earlier isn't good enough to deduce the desired inequality with k plus 1 there. So going from our k statement to our k plus 1 statement has actually become a lot harder because our k statement, our inductive hypothesis, is so weak compared to in this first case. So in this first case, even though we're showing an inequality that in theory should be harder to prove, when we try and use proof by induction, the fact that this is quite hard, the fact that this is quite a restrictive inequality, is actually helpful to us because it gives us quite a strong assumption for our proof by induction. And of course there's lots of other ways other than proof by induction that you could prove either of these inequalities, and you could even go about this using proof by induction of first showing this first inequality, and then you'll notice that this first inequality actually just implies the second one. So that's one way of proving the second inequality still using induction. But I think this is really interesting that this illustrates this phenomenon with proof by induction, that even if you seem to have a statement like this first one here that should be harder to prove than this second one, it doesn't quite work that way with proof by induction, because trying to prove a hard statement can actually become easier with proof by induction because it gives you a much stronger inductive hypothesis to work with there. Whereas in the second case, even though in theory this should be easy to prove, because it's a weaker statement, the inductive hypothesis is weaker, which makes it harder to go from your k statement to your k plus 1 statement as part of your inductive proof.